Welcome back, everyone, to the Deep Dive. You know, we love to get our hands dirty with the latest research, and today's no different.
No, not at all.
We're going to be digging into hybrid quantum classical machine learning.
Sounds pretty intense.
It is, but also super fascinating. I mean, you hear quantum computing, and you think, okay, Star Trek stuff.
Right.
But it's becoming more and more real.
Absolutely.
And the applications, from medicine to materials to finance, it's pretty mind-blowing.
Yeah. And what's interesting is that we're not talking about quantum computers completely taking over.
Right.
It's more about how they can team up with the classical computers we use every day.
Yeah, exactly. It's like this hybrid approach.
Mm-hmm.
And we're lucky enough to have a fantastic essay by Jorgo Schneppat to guide us.
Oh, Schneppat's work is always insightful.
It really is. And this one's hot off the press, January 2nd, 2025.
Oh, wow. So it's really cutting edge.
Oh, yeah. So first things first, for our listeners who might not be totally familiar, let's do a quick recap of classical machine learning, just to set the stage. I mean, we see it everywhere, right?
Yeah.
Netflix recommendations,
Right.
medical diagnoses, spam filters. Essentially, it's about teaching computers to learn from data and make predictions.
Exactly. Recognizing patterns, making decisions based on what it's learned.
So where does quantum computing come in? I mean, it's kind of hard to grasp, right?
Yeah, it is.
Like this whole other level of computing.
It really is. It's almost like, imagine a coin.
Okay.
In the classical world, it can be heads or tails.
Right.
But in the quantum world, it can be both at the same time. Yeah. It can explore all these possibilities simultaneously.
So much more powerful then.
Oh, incredibly.
And that's where this idea of hybrid quantum classical machine learning comes in?
Exactly. Using the strengths of both. And that's
Right.
what Schneppat really digs into in this essay.
And he calls it a bridge between classical and quantum computing.
Mm-hmm.
So how does that actually work?
Well, I think a good place to start is by understanding that quantum computers, they're still in their early days.
Right, they're not quite ready to take over the world just yet.
Not quite, no. But they're really good at certain types of tasks.
Okay,
And that's where this hybrid approach comes in.
so it's like a tag team.
Yeah, exactly. We use quantum computers for the things they excel at,
Uh-huh.
and classical computers handle the rest.
Okay, got it. Like delegating, playing to each other's strengths.
Exactly.
So what are these quantum superpowers we're talking about? What can they do that our everyday computers just can't handle?
Well, one of the big ones is simulation.
Okay.
Quantum computers can simulate things at a level of detail that would take classical computers, years, maybe even decades.
Oh, wow. So we're talking like simulating molecules for drug discovery.
Exactly. Or new materials. It's pretty incredible.
Yeah. And I'm guessing that's where these variational quantum algorithms, or VQAs, come in, right? Schneppat mentions those quite a bit.
Yeah, he does. And they're a really good example of this hybrid approach. Imagine it like this, the quantum computer is running all these different experiments trying to find the best solution to a problem.
Yeah.
And then the classical computer analyzes the results and it tells the quantum computer what to tweak next. It's like a back and forth.
So the quantum computer is like the experimentalist,
Yeah,
just throwing stuff at the wall and seeing what sticks.
exactly. And the classical computer is like the supervisor.
Okay, got it. Analyzing, refining.
Exactly.
So it's this beautiful partnership. And Schneppat seems pretty excited about the potential here, right?
Oh, definitely. And I think for good reason. But let's maybe dive into some of the specific applications Schneppat highlights in his essay, because that's where it really gets exciting.
Yeah, let's get to the good stuff. What can HQML actually do for us in the real world?
So Schneppat really emphasizes the potential of HQML in medicine.
Okay, yeah. Medicine seems like a natural fit.
Absolutely. He talks about speeding up drug discovery,
Right, like what we were talking about with simulation.
Exactly. Being able to simulate how molecules interact, that could shave years off the drug development process.
That could be huge. And I think he even mentions personalized medicine.
Yes. Using HQML to tailor treatments to an individual's genetic makeup.
Wow, so instead of a one-size-fits-all drug, you could have something specifically designed for you.
Exactly. And that's just scratching the surface. Schneppat also talks about material science.
Oh, yeah. Material science, that's another area where quantum could really revolutionize things.
It really could. Imagine designing materials with specific properties like strength or conductivity.
Right.
Yeah.
Building them from the ground up, atom by atom.
Exactly. Things like lightweight alloys for airplanes or super efficient solar panels.
That's amazing. I mean, it sounds like science fiction, but it's becoming reality.
It is. It really is. And then there's finance.
Oh, right. Schneppat mentions that too.
Yeah, using HQML for things like risk management or portfolio optimization.
I could definitely use some help with my portfolio.
I think we all could, but seriously, the potential there is huge, making investment decisions with incredible speed and accuracy.
Yeah, it sounds almost too good to be true. But okay, let's be real. There have to be some challenges holding all of this back, right? I mean, quantum computing is still pretty new.
You're absolutely right. It's not all sunshine and roses. Schneppat actually dedicates a good chunk of the essay to discussing these challenges.
Well, good, because I was going to say, it can't be that easy. So what are the big roadblocks?
Well, for one, quantum computers are still incredibly delicate.
Okay, yeah. I've heard they're very sensitive to their environment.
Exactly. Even the slightest disturbance can cause errors. It's a big engineering challenge.
So keeping them stable and running smoothly, that's a big hurdle.
A huge one. Schneppat even compares them to these high-maintenance race cars. Incredibly powerful, but prone to breaking down.
I like that analogy. Makes sense. So, what else besides the whole delicate race car thing?
Well, then there's the issue of integration.
Right, because it's not like we're just going to ditch all our classical computers overnight.
Exactly. So we need to figure out how to make these two very different types of computers work together seamlessly.
That sounds like a pretty big puzzle.
It is. It involves developing new programming languages, new algorithms, really rethinking how we approach computation.
So it's a hardware challenge and a software challenge. Fun times.
Yeah. But hey, challenges are what make it interesting, right?
Right. I mean, if it were easy, everyone would be doing it. So are there any other big challenges Schneppat brings up?
Well, he does talk about the ethical implications of HQML.
Oh, right, of course. With any powerful technology, we need to think about how it could be misused.
Exactly. And Schneppat emphasizes the importance of responsible development.
Yeah, making sure this technology benefits everyone, not just a select few.
Exactly. It's something we need to be thinking about now, not after the fact.
I agree. So a lot to consider. But despite the challenges, Schneppat seems pretty optimistic about the future of HQML.
He does, and I tend to agree.
So you're saying it's not all doom and gloom?
No, not at all. I mean, yes, there are challenges, but the progress being made in both quantum computing and classical machine learning is incredible.
So you're hopeful?
Definitely hopeful. We're just at the beginning of this journey, and who knows what amazing things we'll discover along the way.
So we've talked about the potential of HQML, the challenges, the excitement. But I think it's important to step back for a second and ask ourselves, why does this all matter? Why should our listeners care about this stuff?
That's a great question. And I think Schneppat really hits the nail on the head in his essay when he talks about HQML's potential to solve some of humanity's biggest problems.
Okay, so we're talking big picture stuff here.
Exactly. We're talking about things like curing diseases, developing new clean energy sources, even tackling climate change.
Wow. So not just making our phones faster or whatever.
No, this is about using technology to make a real difference in the world.
I like that. It's inspiring, actually. But Schneppat also cautions against just blindly rushing into this new era, right?
Oh, absolutely. He's very clear about the need for responsible development.
Right, because with any powerful technology, there's always the risk of unintended consequences.
Exactly. And HQML is no different. We need to think carefully about the ethical implications. Who has access to this technology? How do we ensure it's used for good?
Yeah, those are big questions. And I appreciate that Schneppat doesn't shy away from them. So maybe to wrap things up, what are the key takeaways you want our listeners to remember from this deep dive into hybrid quantum classical machine learning?
Well, first, I think it's important to understand that this is a really exciting field with the potential to revolutionize, well, pretty much everything. But second, we need to approach it with caution.
Right, a sense of responsibility.
Exactly. This technology is powerful, and we need to make sure it's used wisely.
Well said. I think that's a perfect note to end on. Thanks for walking us through Schneppat's essay. It's been really insightful.
It's been my pleasure.
And for our listeners, if you want to learn more about hybrid quantum classical machine learning and dig deeper into Schneppat's ideas, we've got links to his essay and other resources in the show notes, so be sure to check those out. And until next time, keep exploring the fascinating world of quantum computing.